So let's say we want to do a hypothesis test, in this case for means, and we're not given the summary data, but we're given the individual data points. So for this one, we're looking at extra math activities in hopes that they increase the performance on an aptitude test. So we have some scores for students who use the activities, so that would be with activities, and then those who did not use the activities. And so the numbers you see listed in those rows are their test scores. So notice that we have pretty small samples. In order to run a hypothesis test, we want to make sure that our samples are large enough. Remember, in general, we need, if we're dealing with means, which we are in this case, right? This is numerical data, so we're dealing with means as opposed to proportions. So numerical data, we're going to need n to be at least 30, and in this case, n1 really to be at least 30, and n2 to be at least 30. So n1, is it greater than 30? No. The same can be said for n2, is it greater than 30? No. So this is trouble, right? We have pretty small samples. We have, let's see, 2, 4, 6, 8, 9 who took the test after using activities and only 8 without. Now the way around this is to say, well, are the original populations normally distributed? We don't know in this case. If you have the original data, right, the full population data, you can take a look at that data, see if it looks to be approximately normally distributed. If so, the central limit theorem tells us that we don't really need to have our sample sizes of 30. We kind of get that normality for free. We're going to proceed anyway. We're going to say, okay, regardless of that, regardless of the samples being a little too small, let's figure this out. So what are our hypotheses? Well, the null hypothesis is that these two means are the same. So we could say something like, mean 1, meaning mu1, right? Population value there. So let me just toss that in and actually use the correct thing here. So mu1, we can say, okay, that is actually equal to mu2. And that's just assuming, right, again, that there's no difference. So the activities did nothing, right? They didn't change the quality or the intelligence of the students at all, their abilities at all. But the alternative is, hey, well, what do we think is going to happen? Okay, well, we think, right, in hopes that this would increase their performance. So if that is the case, we think that mu1, if we're saying 1 is the group with activities, we think that mu1 is going to be greater than mu2. So this is the activities increased performance. From there, we say, okay, cool. So we have all this data. We know that we can run these tests in our calculators. So go to stat, over to tests. Now we got to decide which test we're dealing with. So first of all, we have two samples, right? Two distinct populations, and there's no reason to pair them up, right? The first student with activities, we have a different student who took this test without activities. So no reason to pair those up. So it's not going to be paired data, but rather two samples. And it's a two sample, well, we're either going to choose Z or T. Now in this case, if we're using entirely sample data, that means the standard deviation also comes from the sample. So it's going to be a two sample t-test. We don't have the stats, the summary stats, so we would want to use the data. It's going to ask you for list 1 and list 2. Okay, well, we didn't put the data in those lists yet, so I guess we better go do that, right? So let's clear list 1, and then we'll just put this data in the list so you can kind of go down, right, just putting these scores in one at a time. There are other ways to do this, but this is a perfectly fine method of doing this. Now keep in mind, because these samples are so small, no matter what we get as a result, probably not the most reliable thing. We would want to make sure that we're taking larger samples than this. But even with a small sample, sometimes we can gain some insight, at least a little bit of insight, especially if the results are kind of astoundingly clear. Okay, so we've put all of our data in list 1 and list 2. Let's go back to stat, over to tests, and then, as we said, 2samp t-test. So 2samp t-test, we now have our data in list 1 and list 2. Frequency, we're just going to say 1 for each of those. And then, this is going to ask for our alternative hypothesis. They don't need to ask the null. The null is always the same. So the alternative here is that mu1 is greater than mu2 like we've got. We're not going to pool the data. So then we calculate that 2samp t versus 2samp z. Well, that's our test statistic, right? So our test statistic is t instead of z. And so t in this case is given as 0.555, right? And we could keep going. We should talk about the degrees of freedom, right? The degrees of freedom from the calculator are going to be 14.68. That's sort of a complicated way of doing it. If we use our conservative degrees of freedom, it's the smaller of n1 minus 1 and n2 minus 1. So this is, the smaller of, well, n1, sample size for group 1 is 9. So it's the smaller of 9 minus 1 and 8 minus 1, since the sample size for without activities is 8. So the smaller of those two is 7. So conservatively, we have 7 degrees of freedom. This is telling us we have 14.68 degrees of freedom. Again, that just slightly changes your calculation for t here. We'll use our p-value. So our p-value is going to be the next thing, t and then p. So p equals 0.2936 if we round. But that's a fairly large p-value. So that means, that's, well, it kind of depends on what our alpha level is. But in this case, we'll say since p is greater than alpha, and that's the 5% significance level. So that 5% is saying 0.05, right? So that's maybe a good thing to remind ourselves. Alpha equals 0.05. Since p is greater than alpha, and let me just change this color back, we fail to reject the null hypothesis. There is not statistically significant evidence to suggest that the math activities increased performance on the aptitude test on average. So there are a couple pieces here. The first piece is just, do we reject the null or fail to reject it? P is bigger than alpha, so we don't have very rare results. What we're doing with these tests is we assume the null is true, and then we're looking for some weird occurrence, some small p-value to say, hey, wait a minute, your results are strange if the null is true. Our p-value is big, though, so we don't have anything to say we need to throw away the null. So we are going to fail to reject the null. We are not going to reject the null. So we don't have evidence of the alternative, We were hoping to show the alternative is true. We do not have evidence for that. So there's not statistically significant evidence to suggest that the alternative, which is that math activities increase performance, to suggest that that's true. All right, this is generally how the process works if you have data. It looks very similar to what we would do if we had summary data already, except we just need to put items in a list.